So this first of the two lectures on geostatistics deals with some basic concepts. We'll look at three major things. First, I'll spend some time on the theoretical background and the what we call the geostatistical perspective, is how geostatisticians look at the world of spatial data analysis. Then we get a little technical. We talk about the main tool of geostatistical analysis is the variogram, which is both an exploratory device and actually a statistic of the data, a summary statistic of the data. And then we move from the variogram as a descriptive device to the variogram as a model that describes spatial autocorrelation in the data. So this moves us on to the spatial autocorrelation that we'll see for the lattice data in the last part of the course. Geostatistics is all about modeling spatial random fields. And as we've seen earlier on, the distinction between geostatistical analysis and what we've seen before, the event data, is that here the random variables are considered to come from a continuous, smooth surface. And the problem is the following: because it is a continuous surface, there is no way we can measure it at all possible points. So we have a small finite number of sample points, and from those sample points we will try to infer what is the model, what is the process that generates a surface. So it's similar again to what we did for the point patterns. In the point patterns, we also didn't have the usual statistical framework with the sample population setup, but we had the events, we had all the events, what we call the mapped pattern, and from that we tried to infer what the process was that might have generated these events. So here we're looking at a process which is formally defined as a set, that's these round brackets, of random variables z indexed by, in very general, an index s, where s is some kind of spatial index that is a subset of some larger continuum. And for our purposes, we will only be interested in 2 dimensions. But there's absolutely nothing that prevents this from being generalized to 3 and even higher dimensions, at least conceptually. 3-dimensional analysis is common in geology and earth sciences. Petroleum exploration is one of the main applications of mining. It's actually one of the main applications of geostatistics, and that's in 3 dimensions. But we'll just deal with 2 dimensions to get the main ideas down. So the main idea is we have a finite set n of sample locations. So we call them S1, S2, Sn. And at these sample locations, we measure a random variable z at S1, z at S2, z at Sn. And then what we're trying to do is, from this information, try to figure out what is this process here. What is it that drives the variability of the magnitudes in z over space? And just to give you an example, this is also one of the sample data sets. It's the Baltimore data set on the Sal site. This is a sample of locations of house sales transactions. So the sample points are the addresses of the houses. The z that we observe is the price of the house, so darker is higher price. The purpose is to, if you wish, fit a model for a surface of house prices to this, so that, in other words, we can interpolate or predict house prices for any location that is not observed. And this is one common application of geostatistics in, say, assessment of house values. You don't have sales for every single house, say, in an urban area, but you have a sample of sales every year, and from that sample of sales and characteristics of the houses that you can observe, you can predict what the value would be, the expected value of houses at other locations that didn't sell. and then that can form the basis for your taxation of property tax and so on. Another example that we will be using is air pollution. These are measurements of ozone at about 30-some measurement stations in the Los Angeles basin. So again, this is even more extreme. You only have 30 points. At those 30 points, you have hourly measures, a lot of detail of ozone and other pollutants. And then from those 30 points, you try to predict a surface for the whole Los Angeles basin. So that in principle, this model, if you give me a location, I should be able to give you a predicted value of the pollution at that location. And the way we summarize this, and this is typically the end product of his geostatistical analysis, is a map. Either a map like the previous one, which is a continuous contour map, or a map like this one, which is also called an isoclef map, which is just contour lines. How do we get these? We get these by computing predicted values for a lot of locations. And then we use these to draw contour lines or turn them into a grid to mimic a surface map. So this is very similar to what we did in the point pattern analysis when we had the control points. Remember, the F statistic is distance to a control point. So the software did it for us, but we'd set up a grid of control points, and so for every one of these points, we computed the distance to the nearest event. Here, we will use our model for the surface to predict a value for each of these control points, and then those are used to make a map. You can think of them as grid cells, for example, and then that gives you a continuous looking map. The conceptual framework that we use for this is based on a number of fairly important assumptions. And we already started talking about this a little bit in the context of point patterns. It's the same here, and it's the same in the lattice analysis. The only way we're going to be able to do any kind of meaningful analysis with a simple cross-section is if that cross-section is stable, is in an equilibrium. If you remember, I mentioned before that when we see a pattern of points, the points are not individual observations, but the pattern is one single observation on the pattern. It's the same here, in that we don't have multiple observations, but we have a single realization of the stochastic process, the chance process that generates the values. But rather than events, now these values are a continuous surface. So let's say we're interested in temperature. We want a temperature surface for the whole US. There's no way we can go and measure the temperature at every possible location. So how does this work? There are a number of weather stations. These are points, sample points. They measure the temperature. And then out of that, with a model, you get a nice map for the whole US. Even points where there's no way to get to measure the temperature, you will have a predicted temperature for that location from the model of the spatial process. So in order to do that, you need this notion of stability. And as I alluded to before, basically we're cheating. We're cheating because we start by saying we only have one observation. The pattern is the observation. But then we act as if we have multiple observations. So we act as if each of these points is a separate observation. And the only way we can do this is if we assume that the process is in equilibrium, which we refer to as being stationary. It's a stationary stochastic process. And let me explain more precisely how this works. So the general idea is that we're basically stuck with the single observation. There's nothing we can do with that. But if the process is well behaved enough, then for all practical purposes, we can act as if these are multiple observations. And we can compute averages from the multiple observations as if they are the average obtained from multiple realizations of the pattern. This is really the mental, the conceptual trick. As long as you have a stable process, whether you look at one realization of that process or several realizations of the process, it doesn't make any difference. They're all basically the same because the process is in equilibrium. They're not exactly the same because there's randomness involved. But taking away the randomness, they are the same. It's as if you had a regression with an error term. The error term is the randomness. So the regression is the same. It doesn't change. But because of the error term, you get different realizations of the predicted value. So the randomness only comes from the randomness of the error term. And so by restricting the randomness of the process, we will be able to analyze this. And this is a picture that I got out of a book on ValueWin, which is a software I used to use in this class, but it's not further developed, so I switched to the newer stuff. But in his book, Panetier shows a I think, one of the best examples to illustrate this. And this is exactly what I just said. Assume we can actually observe multiple realizations of this process. Then we can conceptually think of the one that we observe as being 1/3 coming from the first realization, 1/3 coming from the second, and 1/3 coming from the third. And you can keep cutting this up in smaller and smaller pieces until you are at the point that each individual location can be treated as if it was a realization from a separate map, if you wish. But because all these maps are basically the same, you can just take them together and then go back to the usual analysis. But in order to get there, you need this requirement that each of these maps is basically the same. And in order to guarantee that that works, it's an assumption. There's no guarantee that this is actually the case for your actual data. We need to formalize this. We need to formalize what we actually mean by this map being the same each time. And this is where we formalize the notion of stationarity in terms of moments of the distribution. Now, for those of you who are not familiar with this terminology, a moment is a characteristic of a distribution. And the first moment is the mean. The second moment is the variability around the mean or the variance. The third moment has to do with the symmetry of the distribution or the skewness. The fourth moment has to do with the thickness of the tails of the distribution. In other words, how likely are extreme observations? That's what the tails are about. How likely is it that you get very large positive or negative values? And so on. The fifth and the sixth moment are used in theoretical derivations, but in practice hardly ever computed. But conceptually, you can keep going on. And they're all basically deviations from the mean raised to a power that matches the moment. So the first moment is the mean. Second moment is the square deviations from the mean, and so on. So these moments, you can fully describe a statistical distribution by all the moments. Now, that's not practical because there's too many of them. So what we want is distributions as mathematical simplifications that can be characterized by a few moments. And that's where the normal distribution or the Gaussian distribution comes in play, because it can be fully characterized by the first and the second moment. So you don't even need the third moment or the fourth moment. If you have the mean and the variance of a normal distribution, you're done. Now, this is not the case for other distributions. To characterize other distributions, you may need more moments. But the principle is the same, is that rather than having to compute an infinite number of these moments to characterize the distribution, we like to work with distributions as mathematical formulations that can be characterized by a few of these moments, Because we can compute these moments. We can take our data and get the average. And then with the average in hand, we can compute a variance, and so on. And if we know how these moments behave for the theoretical distribution, we can learn something from our sample moments about the theoretical distribution. That's what it's about. And we'll do the same for our spatial data, but in order for that to work, we have to constrain. And basically the constraints are twofold. They're restrictions on how much spatial dependence we can have. And this is where we go back to our Tobler's law. We have to have some form of distance decay. We cannot have that everything depends on everything else equally strongly. We have to have some way that says, if you move far enough away, then there's no more correlation. That's the essence. Now, how far is far enough? That's a different story. That is a characteristic of the data. But in principle, theoretically, we must have a structure of the dependence that decays so that you can achieve, for all practical purposes, lack of correlation as long as you take your points far enough or your observations far enough apart. That's what it's all about. The second thing we have to limit is variability. If things vary too much, then you really don't know what is going on. Let me give you an example of a bimodal distribution. A bimodal distribution is one that has 2 points along which the values concentrate. Say, if you have a neighborhood with low-income people and high-income people, it has 2 modes. You have the mean for the low-income people and the mean for the high-income people. If you throw them all together, you get a mean of a mixture, but you get a high variance around that mean. So a high variance can be an indication that there's actually 2 different processes going on, and we don't want that. Because of our requirement of stationarity and stability, we want to have a single process data. So we need constraints on this. We need, this is a theoretical requirement. People often ask me, well, why would you even say that the moment has to exist? Well, there are cases where they don't exist because you can't compute them. For example, chaotic type of phenomena, or situations where you can have infinitely large numbers with less than infinitely small probabilities. Those are situations where you cannot, the mean does not exist as a mathematical concept. So before we even get started, we have to make sure that all these things do exist. So this is basically cutting out weird phenomena. Now, if what you're interested in happens to be one of these weird phenomena, then you're in trouble, of course, because you've just assumed them away. Okay. The other things will be a little more concrete, because they will have to do with the first moment or the mean of the process, the second moment or the variance of the process, and the correlation or the covariance of the process. Before we go there's another concept that you might see in the literature and that I just want to spend one moment on because it ties back into this example I gave you with the different map layers, is this concept of ergodicity. And essentially it means that it doesn't matter which one of these possible realizations you actually have in front of you, because they're all the same. So if you specifically want to compute an average, ideally, since each map is one observation, we would want multiple maps, and then we would compute the average from these multiple maps. Well, what ergodicity tells you is that you don't have to do that, because the average you get from your single map is just the same in terms of information content as if you had multiple maps and computed the average from that. So again, it's a structure, it's something that takes away variability from the process. And these things are all conceptual. They give you a mathematical basis to analyze this. Don't try to necessarily imagine this in real life, because most of the times it doesn't exist in real life. You know, in real life, you know, you don't have multiple maps. You have one map. So it is about building the mathematical framework that allows you to do statistical analysis with that one map. And this is the theory of stochastic processes. You know, time series are the same. You may not think about it, but if you're looking at a time series, which is quote-unquote history, there's only one history for you to look at. That's the one that actually happened. But the way stochastic processes look at this is only one of many possible histories that could have happened. We just see one of these, and what we try to figure out is what is the process that generated this. And it's the same setup. You have to assume some structure, because otherwise you're stuck. You have one observation, that's the history that you observe. You have one observation, that's the map that you see. And the whole essence of the stationarity business is that even though we only have one map, we can act as if we had multiple maps. And we took one piece from one of these maps, another piece from another one of these maps, and they all ended together in this map that we have in front of us. And for all practical purposes, it's the same thing. That's what stationarity is for. Okay, most formally, the stationarity pertains to the complete distribution of all the points. So in spatial analysis, this is always a multivariate distribution. This is not a single variable, but this is a random variable at all the locations taken together. So what stationarity means, in essence, is that it doesn't matter which subset of these data points you're looking at, because their joint distribution is the same no matter where you are. So if you think of the US and all its weather stations, and assuming stationarity, which is of course totally unrealistic for temperature, for example, but let's just, for the sake of the argument, assume that this is stationary. Then what this is saying is that the characteristics of the distribution of temperature over space would be the same if we take a bunch of stations in New England, or a bunch of stations in California, or a bunch of stations in Texas. It doesn't matter. That's a very strict requirement. And what we're going to do about this is make this operational, because it's not operational. You can say something about the joint distribution, but you can't see it. Okay? I mean, when you look at a phenomenon, you make statements like, this is a normally distributed random variable, but you can't actually see this. Think about what you do. You compute the mean, you compute the standard deviation, then you stick it in a formula, and then you get your nice bell curve. Okay? But you don't actually see the bell curve. That bell curve is something that you construct from the moments and the equation. Take away the equation, you're stuck. Okay? So talking about joint distributions being the same no matter where you are is very nice from a theoretical mathematical point of view. In practice, it's useless. So we're going to make this practical by translating this requirement into requirements for the things that we can measure and estimate, which are these moments. So if we can translate what this means into what it would mean for the mean, the variance, the covariance, then we're in business. Let's say, and this is one of them, stationarity, moment stationarity is defined in terms of stationarity of the mean. In other words, the mean is the same everywhere. So in practical terms, what we can do now is we take our stations in New England, compute the average temperature. Take our stations in California, compute the average temperature. And those two should be the same in a statistical sense. Obviously, they're not going to be identical, but given the variability, they should be the same. That's what this moment stationarity means for the first moment or the mean. Okay? So the requirement theoretically is that the distribution, the joint distribution, is invariant under spatial shift. and we will translate this into a specific moment condition, namely that specific moments are invariant under spatial shift. The mean has to be constant no matter where you are. So there's no trend. No places where the temperatures are systematically lower than other places. They're the same everywhere. No places where the pollution is lower than it is elsewhere. Now you might say, well, why would I want to bother with a process that is like that? This is not an interesting process. The mean is everywhere, the same. So why would I be interested in this? You're interested because you get there after you model part of the process. So as we'll see later, these assumptions are applied to the residuals of the model. Let's say we have something that predicts the temperature, say in function of latitude and longitude, a trend surface. Okay? The trend surface obviously is not constant because depending on where you are, you get a higher or a lower temperature. But the error term for that trend surface, since this is a random error term, its mean is 0. And its mean is 0 everywhere. So this error term is something that is stationary in the first moment because the mean is constant everywhere. And we'll use the same logic for the other moments as well. The variable itself may not satisfy that requirement, but after we apply a model to it and we get an error term or a disturbance term, then we apply that requirement to the disturbance term, and that's all we need. So as we'll see later when we talk about kriging and spatial prediction, in essence this is about two types of models. The model, what geostatisticians call the large-scale trend, which we would call, say, the regression model or the signal. And then the model for the error term or the noise. These requirements pertain to the model for the noise, not to the model for the large-scale trend. So you can have a model for a changing mean, but then the error term has a mean of 0, which does not change. And same for the variance. So for the variance to be stationary, we cannot allow heteroscedasticity, which is non-constant variance. So the variability around the mean has to be the same everywhere. In other words, the precision of your model has to be the same everywhere. You can't have a model that's more precise in some regions than in other regions. So you can't have a weather forecasting model that does better for the colder weather than it does for the warmer weather. Okay? It has to be the same no matter what the weather is. That's what these requirements mean. And then the last one is a little trickier to imagine. It has to do with the covariance, how random variables covary in different locations in space. And here again, we put in a requirement that this covariance, which later we'll call spatial autocorrelation, has to be the same no matter where you are. Now, what does that mean? What does it depend on then? It depends on how far apart you are, and it depends possibly on the direction, on the angle between two observations. So the only things that are allowed in here to affect the covariance, which is the strength of the joint relationship between two observations, is how far apart they are and maybe the angle that they form between them, but not where they are. So same thing, if I take two stations that are 5 miles apart in New England and look at their correlation, and two stations that are 5 miles apart in California and look at their correlation, it should be the same correlation because it's driven by the 5 miles, not by the fact that you're in New England versus California. So that is what these requirements build in as restrictions to the processes that we can model. And with this in hand then, we're actually in pretty good shape because then we have enough restrictions on the process that we can play our con game and we can act as if we actually have multiple observations even though we only have one map.